Okay, welcome everybody. Good morning. Good morning to the people tuning in from Zoom. I don't know if somebody else joined. I didn't see the Zoom link anymore. Yeah, I'm very, very excited to present MCTDH and MCTDH-X to you today. Yeah, question. I'm already recording. Yeah. Yeah, I've talked about this method for like a year and a half to several of you, and I never really introduced it properly, apart from some presentations by me and Julia. But today is the day where this happens, so I'm very excited to be talking about this. So just a couple of technical information. So we're going to have two breaks, one in the morning, one in the afternoon. There's fika outside. And then we'll also have lunch provided. There's going to be some wraps that will be delivered around noon. If you have any questions during the talk, just ask away. It's supposed to be very informal. Also in Zoom, if there are questions, just unmute yourself and ask. And then the structure will be, I will give you 3 lectures, one about the method at large, one about the software, and one about what we're doing with the software nowadays. And then in the afternoon, there will be a hands-on session. I hope everybody was able to install the program. Well, there are at least 1, 2, 3 people who have the program installed, so then we can kind of like work on it. It can help if it didn't work. Okay, so we can start with the first presentation, which would be about the method MCTDH. And I just found out that Osa already knows about it and uses it. So it's very good. There's already users of the method in the room. So let's see if this works. All right. So maybe let's start by trying to spell out MCTDH, because it's a bit of a mouthful and people never really remember what it means. So MCTDH, the MC part stands for multi-configurational. And yeah, maybe just one step back. MCTDH is a method that is used to solve the many-body Schrodinger equation. So we use it to just solve dynamics and ground state problems in many-body physics. Participants can now see your screen. Okay, I hope they were able to see it before as well. So, so in the term MCTDH, MC stands for multi-configurational, and by that I mean that we use a set of configurations, linear combinations of configurations, to expand the wave function and to describe the problem in that way. So you can imagine a configuration as a set of a partitioning, if you want, of the wave function. So in this figure, the dots are the quantum particles that are interacting with one another, and then you find a way of describing them with these partitions. This could be one configuration, but there could be another, there could be yet another, and so you have to use a linear combination of all these different configurations to expand your wave function, and that's where the MC multi-configurational comes from. Then the TD stands for time-dependent, because the configurations can change in time. They're time-dependent quantities. And in fact, the method adapts the configurations or the construction with the configurations to the time evolution itself. So that's why we have TD, time-dependent. And finally, Hartree, the H, it comes from Hartree. Hartree comes from the Hartree approximation, which is a technique that was developed in the 1920s already by Hartree, hence the name, in which you describe your wave function as a product of single particle wave functions. And so in this case, also the name is derived from this kind of idea of constructing products. And so the configurations in this case, not just the wave function itself, but the configurations will be constructed as Hartree products of single particle functions, what we will call orbitals during this day. So by using the sketch from before, this means that each configuration can be represented as products of single particle wave function that can contain one or several particles in themselves. So this is just to give you an idea of where the name comes from. Now, what does it do? So I just briefly mentioned at the beginning that it's used to solve the many-body Schrödinger equation. So the main goals of the approach is to, one, represent the many-body wave function efficiently, and also to adapt to time-dependent problems. The second point is to be able to handle interacting systems, even ones with long-range interactions and correlations. The third point is to describe both time-independent, but mostly time-dependent problems, even with time-dependent Hamiltonians. So you can describe quenches, periodic drives, and any kind of time dependence you want. The fourth goal is capturing correlations. So this, as we will see, it's beyond mean field method. So you're able to capture correlations across different particles. So it goes beyond what we know with Gross-Pitayevsky or Hartree-Fock approximation. And then the fifth goal is to adapt to different dimensionalities and systems seamlessly. So if you think about, for instance, MPS in quantum physics, that is really tailored to one-dimensional systems. Can also apply to 2D, but it's a bit more fidgety. So MCTDH, the construction itself is dimensionality independent. So it can be applied to any type of dimensional problem you want. Okay, any questions so far? Or is it clear?
You can see that the configuration is this TD, that you update the basis you're using.
Yeah, we will see it later.
Will you update it also for the time-independent cases? Will it be updated automatically?
It's updated in imaginary time. So if you want to go to ground state physics, then you do the same update, but it's in imaginary time. So you go from like an excited state to a ground state. Yeah. And also Lucas raised his hand for no. It was a thumbs up. Okay.
It works at a fixed number of particles, right?
Yes, yeah, fixed number of particles. We'll see also later fixed number of orbitals. So you first have to define how many particles you want to describe and with how many orbitals. So the kind of computational complexity, and then those are fixed, and then you can do your optimization.
The external drive doesn't have to be periodic, it can be anything.
It can be anything. It can be quenches. Yeah, I worked quite a lot with quenches in the past year. So you prepare your states, your ground state in a certain state, and then you quench it to a different Hamiltonian with a different structure, for instance. And then you see how it evolves in time. So where it is used, here I just give 5 main fields where it's very popular. It originated in quantum chemistry, as we will see. So that's it's still very much used in that context to model molecular vibrations and so on. It really had a boom then in the 2000s to describe ultracoatomic and molecular systems, in particular bosonic ones. And this is where I kind of came in with my research. It can be used also in certain condensed matter settings in descriptions of bosonic Josephson junctions in cavity QED. So this is, again, kind of a branch of ultracold AMO physics, where you additionally put your atoms or molecules in a cavity and you shine a light on it, and then you see how the light and matter behave with one another. And then there is also uses in open quantum systems, in particular the multi-layer version of MCTDH, which we will not really discuss in detail today. I would just give you kind of like a glimpse of it, but that's where it's quite powerful. And today we will mainly focus on this kind of lower 2 fields. Okay, so that was just a brief introduction in the topic at large. So this brings me to the outline. We will first talk about a bit of history, how the method came about and who was involved and so on. So from the origins to the transition to quantum physics, and then the new generation of the method and of the code. Then we will dive deeper into the ansatz itself. I will explain how you construct this kind of decomposition, how it's applied to the many-body Schrödinger equation, what is the variational ansatz, and how you construct the MCTDH action to come up with the equations of motion. And then we will talk about the equations of motions themselves. We will try to kind of find an interpretation for them and look at some special cases. And then we will talk about the capabilities and limitations of the method. and also how to solve the equations of motion in practice. Okay, so without further ado, actually, I have a disclaimer first. There will be people mentioned in this talk. There will also be people not mentioned, but who still contributed a lot. I had to kind of summarize a bit, so I apologize in advance if I forget some, important people who are working in MCTDH or MCTDH-X and who contributed to the code. I just made like a quick summary of the history. So if you see faces and people, those are not the only contributors to the method and the code. So the origin story starts actually pretty far away. It's in the 1990s, in 1990, to be more precise, with the seminal paper by Hans-Dieter Meyer, Uwe Mante, and Lawrence Zederbaum, who were all quantum chemists working in Heidelberg. Here they are. So they were looking at the time for a way to model molecular vibrations and reactions in certain small classes of molecules. And the method of choice at the time, the standard, was to use time-dependent R-tree, which is a method in which you take your many-body wave function and you simply decompose it into a product of single particle wave functions. So it's kind of like a mean field treatment, a mean field approximation. The problem is that being mean field, it does not allow you to treat correlations. And then, so if you want to look at molecules that have strongly coupled degrees of freedom, like benzene or molecules where the electrons are highly delocalized, this will not be a very good approximation. So then the new idea that they had was to construct a superposition of time-dependent coefficients. So basically, what they did, they just added here a sum with some coefficient that is time-dependent, as you see here, t. And then they made all the single particle wave functions also dependent on the selection of the different configurations that you can have. And so note that in this formula and all the other ones, everything is time-dependent. So everything is a function of time. So with this, I will explain later then exactly how you construct the equations of motion and so on. But just to give you an idea, with this method, they were able to handle quickly much larger systems that we're able to do before with up to 24 degrees of freedom. It was applied to different types of dynamical processes, such as photodissociation and dissociations on surfaces, and also just to calculate the entire vibrational spectrum of small molecules. So they started with something small, like an OCL, and then they quickly moved to larger and larger molecules, such as pyrazine and benzene and so on. And they were able to describe many different dynamical properties of these molecules with this method. So for around 10 years, it was mostly focused on quantum chemistry and applications in that field. So the degrees of freedom that we were looking at were distinguishable, like vibrations in different vibrations in a molecule. But then at some point, they asked the questions, what about indistinguishable particles, like proper quantum particles like bosons and fermions? And so historically, the fermionic version was developed first by Ottmar Koch, Armin Skrinzi, and Wolfgang Kreuzer. They're all laser physicists. They published their first paper in this Laser Physics 13 in 2003. And the main idea there was to just add a very tiny modification to the ansatz, and that is to anti-symmetrize the wave function. So just to add this operator S that takes care of the anti-symmetrization. Yes?
What are laser people doing with bosons? With fermions? I was expecting to bosons.
Well, they are looking at the dynamics of fermions, so electrons essentially in molecules that they were exciting with lasers. So trying to see how they respond to that. And so it's important to note that now, because you have this anti-symmetrization operator, the configurations become Slater determinants because you're dealing with fermions. So what you really have in this decomposition is a time-dependent superposition of Slater determinants that then are optimally optimized in time. So fermions came first originally in 2003, and then there was some work published in a couple of years later, but then kind of, as far as I know, it kind of died out a bit. But then in 2006, the Heidelberg crowds, in which case consisted at the time of Ophir alone, Alexei Steltsov, and Lorenz Zederbaum still, who developed the original quantum chemistry method. They thought, okay, people have applied it to fermions. What about the bosons, right? They're also indistinguishable particles. And here, the idea is to simply, instead of using the anti-symmetrization, to do a symmetrization procedure to obtain the correct quantum statistics of the particles. And now, in this case, the configurations become permanents instead of Slater determinants. So you have a linear combination of time-dependent permanents that you use to describe your many-body state. And here there is a huge advantage, and that's why the field became very popular. It's that bosons condense. Fermions do not. So for fermions, you need to have many more orbitals, single particle wave functions to describe many particles interacting. But for bosons, you do not need to have as many. Because if you want to look at behaviors slightly away from condensation, so fragmentation, or how, for instance, a BC, a Bose-Einstein condensate, behaves when you raise a barrier in its center, then typically, if you're only looking at those very strongly condensed systems and just slight deviations away from it, a lower number of orbitals will be sufficient to describe the behavior correctly. And so you are able to go to a much larger system sizes beyond this kind of Kroos-Ptoyevsky mean field theories that were used at the time. And so they applied it to many different kinds of systems. Like I mentioned, BC fragmentation. So they were looking at a BC in a trap, and then how the BC responds to a barrier being raised in the center of the trap. So typically the BC will fragment, so it will decompose or split into different blobs. And then you can also think about this type of construction, so with the two wells, the two sides of the wells, as the two sides of a junction where there is tunneling in between. So that can kind of correspond to a Josephson junction, but with bosons instead of fermions. And they were also looking at the physics of it and the dynamics. They were also looking at dynamics of BCs themselves with time-dependent fields or also quenches, like we said before. And another area of interest was the formation of vortices in rotating BCs. Because the composition is time-dependent, you can create any type of one-body or two-body interaction. So you can also place particles in rotating or moving environments. And so you can describe, for instance, rotating BCs or the process of taking a BC or superfluid, putting in a rod, and then stirring and see what happens if you can create vortices and so on. So this was a very successful area of research due to this method.
I remember one paper that came also around 2006, and they did the Bose-Hubbard model.
Mm-hmm.
And when you increase the interaction, you actually start to populate higher bands.
Yeah.
And then this method captured that.
Yeah. So I didn't really say, but this method. So I will always today I will always use it in the continuum. But the composition itself, you can also apply to a lattice system, to a discrete system.
They did continuum there.
Yeah. But the composition in itself, it's not really restricted to a given representation of the wave function. So just a brief recap, it started in the 90s in quantum chemistry, then in the 2000s it moved to quantum physics with MCTDH-F and MCTDH-B later on. But then every one of these people kind of developed their own software. And so there was not a lot of intercommunication between them. So then the birth of the modern software MCTDH-X, and the one that you use in the afternoon, starts really in 2014 with Axel Lode, who was also in Heidelberg at the time and was working with Ophir and so on. So he kind of put together the protocode that was developed by Alexei, MCTDH-B. and then have really, pushed it to a new level. And then 2 years later, with Elke Fasshauer, they added the fermionic part. So they merged the fermionic code and the bosonic code. As we saw before, the only thing that changes is the symmetrization that is different between the two. So they naturally can kind of be combined. And then Axel also added the possibility of adding particles with internal degrees of freedom. In this case, speedron condensates. Right now, what we are doing is to add like full spinful fermions to the code. So right now, it's really kind of like a very generic, very overarching code that can describe a lot of different types of systems. So this was the birth of what we know today as the MCTDH-X software. Then kind of we came along, me, Luca, who left academia, Luca Papariello, Ray. We kind of started working with our supervisor on Bose-Einstein condensates and cavities. So we collaborated with Axel in kind of extending the method to also include the interaction with cavities and so with light fields. And this is very useful because there were a bunch of experiments going on at the time where you were really looking at the behavior of BCs that are irradiated with lasers, and then see how it behaves when you put them in a cavity. So if you think about shining a light on this BC, then there is some scattering process that occurs when the light scatters on the atoms. And then some of the light can be reflected into this cavity and can bounce back and forth. And then, so this induces some effective long-range or even infinite-range interactions between the atoms that can lead to many interesting properties and novel fluids of light and matter that combine both the atomic and the photonic degree of freedom. And also because the method is time-dependent, you can engineer any type of protocol that they do in the experiments. So you can think of ramping up laser pumps, doing some type of periodic drive, ramping it down. So you can really just recreate exactly what they do in the lab. So it was very useful for us in this context. So a couple of works that we did during that time was to look at parametric instabilities. So when you drive lasers periodically in time, looking at the transition between superfluid to Mott insulator in BECs. We found her hierarchical superfluidity and also really pushing the strength of the interactions to the max. You can even make, in a 1D setup, you can make the bosons completely separate from one another and make them behave like fermions. You can fermionize bosons. So there was a bunch of work with cavity BEC, cavity QED that happened in the late 2010s. I just want to give you, so that was kind of like an overview of MCTDH-X and how it came about. I just want to give you one little note on a different usage of MCTDH, an extension. It's called the multi-layer MCTDH or ML-MCTDH. We keep adding letters to the acronym. So this is a very powerful extension of MCTDH where the system is represented in a hierarchical structure. And by that, I mean that the decomposition itself, you don't take into account all the configurations, but you construct a tree structure of the configurations that are of interest to you. And these can represent different levels of degrees of freedom. So you can describe, that's why the multi-layer term. So you can describe degrees of freedom that occur at different scales, but you can also describe degrees of freedom that are kind of independent from one another. So you can describe systems that interact with a bath, for instance. So you can describe open quantum systems. So this was also developed by Hansi Tamaya and collaborators in 2008 originally. Nowadays, as far as I know, these are the people that work on it the most. I personally don't work on the multi-layer part, but I just wanted to mention it because it might be of interest to you, since I know that some of you work in open quantum systems and so on. So that's something to look into if you're interested. Key applications, I have already mentioned open quantum systems, and generically they're used to deal with larger number of degrees of freedom. So electron transfer processes or quantum transport in nanoelectronics are key applications.
You work with the cavities. Did you eliminate the boson mode, or was that another degree of freedom that you?
So the cavity in our applications is kind of treated semi-classically. So you have an effective action of the cavity on the bosonic degrees of freedom. That does not mean that you cannot take into account the quantum aspect of it, because you can also start from the Hamiltonian, where you have both the atomic and the photonic degrees of freedom. If you integrate out the cavity or the photonic degrees of freedom, you still have a quantum interaction between the atomic degrees of freedom, which kind of inherits the quantum properties from the photons, but the photons are not really there anymore. So you can also describe it like that. But yeah, so one thing that we would like to do in the future at some point is to extend that to a proper quantum description of the light. So by coupling two different species of bosons, for instance, one that is the photons and one is that the atomic degrees of freedom. Any other questions about the history? Otherwise, we move to the actual ansatz itself. So the goal, like I said at the very beginning, is to solve the many-body Schrödinger equation. It can be either the time-independent one, which we get from its spectral properties, so ground states or excited states and so on. But what we really focus on with MCTDH is to solve the time-dependent one, so to get information about the dynamics. And in this case, I wrote the time-dependent Schrödinger equation. Here we have psi. Psi is a many-body state. So it depends on, in this case, I will consider n particles. So it depends on the position of each particle. It's also time-dependent, obviously. And the Hamiltonian, we will consider the one-body term, so a kinetic energy term, Ti, and a potential, one-body potential, Vi, and then all possible pairwise interactions between the particles. In principle, one could also add higher order terms, so three-body terms or combinations and so on, which is not implemented right now in the code, but yeah, one could think of having that as well. So if we want to solve the many-body Schrödinger equation, except in rare cases like the well-known hydrogen atom or monic oscillators, we cannot really do it exactly, so we need to resort to numerical approximations. And there is two main approaches to do that. One is to simplify the Hamiltonian. So we approximate the Hamiltonian with something that is easier to handle. For instance, a lattice Hamiltonian, or we just do sampling with quantum Monte Carlo. Or we restrict the state. So we have only two quantities that appear here. So we can either act on the Hamiltonian and restrict it, or restrict the state itself. And so all the mean field theories like Gross-Pitarievsky and Hartree-Fock are based on this principle, where you reduce the form that your wave function can have. Configuration interaction is another example. And MCTDH also falls into this category of finding a nice, easier decomposition of the state that you can handle. So for later convenience, let me just introduce a couple of notation changes. We will use the second quantization formalism. So we decompose the Hamiltonian into one body part, small h, and a two body part, w. So they are respectively the quadratic part and the quartic part in terms of bosonic or fermionic operators. So the operators are denoted here by a hat. So CK dagger CQ is the two body part. And then here we have a quartic term with four operators. And then operators obey either bosonic or fermionic commutation or anti-commutation relations, which are written here. The matrix elements, HKQ and WKSQL, those are obtained by constructing overlaps with the operators that we introduced before. So the kinetic operator, the one-body potential, and the two-body interaction. And also remember that all the quantities are time-dependent in principle. So the key method that we use to obtain the equations of motion and also to kind of apply our ansatz, which I'll describe in a second, is the variational principle, and in particular, the time-dependent variational principle. So the idea here is you start with a Hamiltonian, which is time-dependent. You construct the Lagrangian from it. And then from the Lagrangian, you construct the action by building the integral over time. And then you want to use the principle of least actions. So you want to find the variation with respect to certain parameters, certain functions. In this case, it would be our type of decomposition ansatz. So you want to find a variation of it that is zero. So you want to minimize the action with respect to a change in parameters. And by doing that, you will get conditions on U, or this kind of functions that you use to write your ansatz. And those will be the equations of motion that you actually solve then numerically to obtain the solution of the state. And interestingly, the Schrödinger equation itself can be derived from such a variational procedure if you use the exact ansatz. So if you use U equal the many-body state itself. So now coming to the ansatz, so we saw kind of at the beginning some kind of summary of it, but I will change the notation slightly to be a bit more consistent with how we write it and we use it in the code. So this is the equation that you have to keep in mind for today. So this is the many-body state. Everything here is still position dependent. I just removed the dependence on R for ease of notation. So you construct your many-body state as a superposition of these what we call configurations that have time-dependent coefficients. So remember that these are n+1 variable functions. So we have n particles here. And of course, time is the additional variable. And these Fock states, so these configurations, are built over a set of m single particle wave functions that we call orbitals, in this way that we saw before with the symmetrization of this Hartree product. So we just make a product of all possible, or of a type one configuration of how you divide this n particles into m orbitals, into this m single particle wave functions. And then you symmetrize it to obtain either a permanent or a stator determinant. Or if you want to write this in quantized language, you take a product of creation operators for a given orbital with a given number of particles in it, nk, that act on the vacuum. And then you have to properly introduce a normalization that depends on whether you're dealing with bosons or fermions. Questions so far about this decomposition? Okay, clear. So then a couple of notes. So this J is actually not just an index, it's a multi-index because it indices all the possible configurations. And all the possible configurations of distributing n particles into m orbitals are considered. So if you look at this sketch, you can think of those colored lines are the possible orbitals. Those are actually just the eigenstate of the harmonic oscillator. And then you can think of placing particles into these different bins, if you want, right? Into these different types of single particle wave functions. You can place 3 in the first one, 2 in the second, 2 in the third, and so on. And then we consider all possible combinations of putting particles into these different bins. So the number of configurations, you can obtain it by just using some simple combinatorics. For bosons, you have to think that they can condense, so you can put multiple particles into the same bin. So you have Bose-Einstein statistics, and that gives you n plus m minus 1 choose n type of number of configurations. This scales much faster to larger values compared to fermions because you have this extra m here. For fermions, due to the Pauli exclusion principle, you can only have m choose n possibilities configurations. Something that I mentioned already before, the only thing that really matters in this decomposition across bosons and fermions is the symmetrization. So you can really treat both bosons and fermions on the same footing. So you do not have to need different methods to describe bosonic or fermionic character. And like we said before, the configurations are Slater determinants for fermions or permanent for bosons. Any questions about that part? Good. Okay, so now we come to the variational procedure. So we saw before that when we want to construct the action, we need to minimize with respect to certain parameters. And in this case, our parameters are, the variational parameters are the coefficients, both the coefficients and the orbitals, because they are both time dependent. So we can both change them in time. So we construct our action by considering all possible configurations. So there is, you know, that number of them, depending on both the fermions. So there is a lot of variables that come into this action. So it depends both on the number of configurations, each configurations, and also on each orbital. So there is m of them. Yes?
But are all the orbitals in the whole already?
No, they are optimized also in time.
So you choose some set of m orbitals out of potentially infinitely many.
Yes.
Right.
So you just choose how many you want to account for.
Right.
And then you optimize them in time. So so if you remember, I said that I removed the space dependence from everywhere, but the orbitals themselves are also functions of R. So you're optimizing them both with respect to time, but also with respect to the space itself. So you can consider them, you can just discretize your continuum space into a vector, and then you're basically optimizing that vector. So the elements of that vector.
Just so I'm understanding this correctly. If you, I mean, you could also choose m position-based states, right? And they wouldn't depend on time. But why these depend on time is because you want sort of the m best vectors to describe the system.
Yeah.
Right.
So if you do what you said, you're doing something called configuration interaction,
Right.
where you basically have the same construction, but it's time independent. And people in quantum chemistry call it configuration interaction. In quantum physics, we will call it exact diagonalization. So you basically take your Hamiltonian and then you just, you know, exact diagonalize it to obtain the instantaneous best basis, which is just the eigenbasis.
Right.
But here it's done in time. Yeah.
So I think, for example, block bands, and you take 2 bands for your calculations.
Yeah.
The wave functions don't change in general, or why would they change? Is it because you're
No, but
changing
because there you're basing it on the. So if you're thinking about block bands, then what you're actually basing it on is the eigenfunctions of the one-body potential.
Yeah.
But this is great if your one-body potential doesn't change. But if there is a change in the one-body potential, or if you also have change in the interactions, then you might want to use a time-dependent basis set.
Okay. So this is because your Hamiltonian is changing in time.
Yeah.
And in his case, you will see that the linear functions there, due to interaction, they will actually get broader.
Yeah.
Positive interaction. So the orbitals will not be exactly.
Okay.
Exactly, yeah. So you're starting from basically a non-interacting picture where you're only considering the one-body potential as your starting point. But then if you add stronger interaction or things change quite rapidly. And this, because you're doing this optimization in time, then at every time step you're trying to find the optimal basis set that kind of molds itself to the instantaneous configurations that you have, to the instantaneous environment, let's say, of the Hamiltonian.
So now you said this is a time-dependent Hamiltonian is the reason that we're doing this, but
you can also do it for time-independent Hamiltonians, but then if you do this variational procedure, you have to do it in imaginary time to get to ground state or slightly excited states. So you cannot really just do an exact diagonalization to get the full spectrum, because you're doing an optimization in time. The action is constructed through the time-dependent variational principle.
right. I think I understand.
You understand? Okay. Okay, so this is the action that we construct by doing the Legendre transformation from the Hamiltonian. You note also that you have here Lagrange multipliers, this mu jk, those are needed to ensure, first of all, that the sum of the populations of each orbital sum to the number of particles you have, so that it's consistent, and also that the orbitals remain orthonormal at all times, so that you do not change them to become non-orthogonal when you're doing the optimization procedure. I mean, this is a detail, it doesn't really come up anywhere in the equations of motion, but it's just important to be aware that there is an intrinsic orthonormality that is preserved.
Is it
yeah.
exactly preserved, or there's some?
I mean, in the end, you do it numerically, right? So yeah, you have to check always that it's preserved.
And you can impose that constraint such that it's exact by using some kind of other constraints on your variation or on your orbitals.
No, I mean, this is an exact constraint, but it's just that when you're doing numerics, then you only have a finite number of a finite memory that you can use to save the information about, you know, how well they're orthogonal to each other. And then once they time evolve, there might be tiny errors that accumulate. And then over time, this might lead to them not being orthogonal anymore. It's more like a finite, how should I say? You do not have, it's like finite errors, numerical errors that creep up, and you need to make sure that they stay small. But it is intrinsic in the variational procedure because we have these Lagrange multipliers. So I think, was it Tommaso who said, yeah, at the beginning, yeah, you have to start with n and then m, and then yes, so those are the givens. So you give a fixed number of particles and fixed number of orbitals, and then with that, you optimize the expansion coefficients and the orbitals to obtain your solution. So it's important to think that you cannot change the number of orbitals midway through. So you cannot start with 10 and say, oh, actually, I need 12, and then continue with 12. So this is a fixed variable you decide on at the beginning, and then you preserve throughout the computation. So you can do then, yeah.
That's a computational constraint of the program, right? Because in practice, it could be useful.
Well, the equations of motion, so you have to do the variational procedure with respect to a certain number of orbitals, right? So then if you change the number of orbitals midway through your computation, you suddenly have more equations that pop up that you need to kind of take into account. So then, I guess in principle, you can just do it dynamically. You just have, oh, now I have one more equation to solve, and then I have to relate it to them. But it's a bit complicated, yeah.
But I mean, I'm just asking, sort of physically, in principle, that could be useful, no?
Yeah.
Okay.
To do it adaptively, where it's like, oh, actually, now the time dependence is changing so much that I need more orbitals. So then, but then it decreases again, and I reduce the number of orbitals. Yeah, in principle, yeah, but it's probably quite an undertaking numerically.
Sure.
Yeah. You also had a question?
I'm not so sure about that, so I want to ask, like, what do you mean by mid-way of the calculations? Like, are there different scripts, like optimization orbitals, and then you can change the
No. So the equations, you do the variation with respect to the coefficients and also to the orbitals, and you get two sets of coupled equations of motion. One is for the coefficients and one is for the orbitals, as we will see in a second. And then you just solve them, with your optimal integrator. But then they are coupled. So you first need to do like a step procedure for the integrator. So you need to first solve a bit of the coefficient equation of motion, and then use the result to plug into the orbital equations of motion, and then solve a bit of that, and then you get, the next step for the coefficient, you solve that again, and so you have to do it like that.
So automatically something I need to kind of like switch.
No, it's done already automatically. Yeah. No, it's highly optimized. It was written first by Alexei in the 2000s, and then Axel worked on it again. So it's layers and layers of optimizing. I'll show then later how the integrator is kind of decomposed. There's like a 7-step procedure. It's highly optimized. So these are the monsters that we solve, the equations of motion that come. So you do the variational procedure, and then you can show that you get this 2 different equations. One looks kind of harmless, The other one is a bit more complicated. So you have to also consider that those are integral differential equations because you have here a derivative, but those terms, rho jk and rho k SQL, those are overlaps. So essentially those are integrals that you need to calculate. So the way to solve those equations is by doing this kind of split method where you first calculate the right-hand side with the guess, then you plug it into the left-hand side, and then you use that to calculate the coefficient equation of motion right-hand side, and then you use that to calculate what is the new vector c, and then use that information to construct the right-hand side of the first one again, and so on. So you have to kind of combine them that way. So to give you a better understanding of all the terms here, so P is just a projector that you need to apply at every time step. Those we already discussed, rho, jk, and rho k SQL, those are the one body and two body density matrices that you have to calculate from the many body state. So you need to have that at every time step. And then for the coefficient equations of motion, H is nothing but the representation of the Hamiltonian in the configuration space. So you need the configurations to calculate that part. So you need basically to solve the orbital equation of motion. And C is a vector that just summarizes, it's an array that contains all the configurations from 1 to n conf. So to solve this equations of motion, actually I'm getting ahead of myself, but that's okay. I will just give you a...
Can I ask?
Yeah.
I have a physics question. In the orbital equation of motions,
yeah.
Can you give me like an intuition of why I am projecting out of the orbitals that I have chosen?
No, not really. I also thought about this, but I don't really understand the reason physically. It just comes about from doing the variational procedure. I'm sure that, you know, if I thought harder about this, I probably could think of something. But right now, I do not know. Yeah, I'm sorry. I cannot give you really like a straight answer right now. Yeah, but what I wanted to just show you, and I'm kind of like getting ahead of myself a bit, but is how we solve those equations of motion. Like we said, they're coupled. So we employ the 7-step integration scheme. And we have different algorithms for different purposes, depending on what type of equation we solve. So the orbital equations of motion is solved usually with the Runge-Kutta integrator. It's fairly straightforward. The coefficient equations of motion instead, this is typically sparse. So we use sparse optimized methods like the Davidson algorithm or the MCS scheme. And this is kind of to go back to the question that you asked, this is how the integrator is described in the code. So there is 7 steps. So the first step is given your initial conditions or initial guess to compute certain quantities. In this case, the one body and two body parts of your Hamiltonian, and then compute the one body and two body density matrices. With that, you insert into the coefficient equations of motion, and then you propagate for half a time step. And then with that, you compute the reduced density matrices for the half time step point. With that, you insert then into the orbital equation of motion, and then you get the orbital also at half time step. And then there is error estimations. So after the second half of time step, there is an error estimation to check whether, you propagate backwards to check whether you have the correct solution. And if it's not, you reduce the time step. And then you do another propagation of another half time step by doing kind of like a similar idea. You just take information from one equation and then you plug it into the other. And then you also do another error estimation check by doing another back propagation to the very beginning. And then if that doesn't fulfill a certain criterion, you reduce the time step. And then you continue doing that until you have convergence, and then you move to the next time step. So this is
But
kind
you
of
don't
like,
know if you have convergence in number of orbitals.
no. This is convergence in the sense of the integration itself. Yeah. This is another point that actually I will mention in a bit. So now let me go back to the picture. So I will take another, we're scheduled to have a break now. I will take maybe another 5 minutes. Is that okay? Okay, so some interpretation of the equations we can have specifically for bosons. It's very nice. We can have a very nice hydrodynamical picture. So for bosons, we have superfluids. For fermions, we can think of Fermi liquids, although it's a bit more fidgety because you have at least at most one particle per orbital. But for superfluids, we can have many particles per orbital. So we can kind of think of one set of nonlinear equations that describe the fluids themselves, so their shape, and then one set for their population, so how much they're populated. And then basically what you do in your decomposition, in your ansatz, you're taking a weighted sum of all these superfluids with the populations. And this kind of picture comes from the reduced body density matrix, which is a quantity that you can obtain. It's kind of like a proxy for density, if you want. You take it by taking the many-body wave function and then calculating basically the overlap with itself, but then you integrate out all the degrees of freedom except from one particle. So you restrict the information about the many-body state to one particle only. And then if you calculate the eigenvalues and eigenfunction of this quantity, the 1 RDM, these are known as natural occupations and orbitals. And these give you information about condensation and fragmentation. So if you have only one natural orbital that is macroscopically occupied, so that is order n, we say that the system is condensed in that state. So it's the only orbital that is populated. But if you have multiple, then you have a fragmented state. So you have this picture that I described before, where you have these multiple superfluids that kind of play with one another to construct the many-body state. So the decomposition that we have is basically, sorry, yeah. So the decomposition that we have is basically the same as this type of natural occupations, but those are time-dependent generalization of that description. And in particular, if you have a very slow override field, then they basically are equivalent to one another. So that allows us to give us come up with this nice hydrodynamical picture of superfluids interacting with one another. Also, it's important to note that we contain in the method other approximations as special cases. If we're talking about bosons, if you consider only one orbital, then we just said that we can consider different superfluids, right? 1m, one orbital, is just a single superfluid that describes the entire wave function. And that is precisely the picture of a Gross-Pitayevsky equation. So where you basically write your many-body state as a product of n equal single particle wave functions. So all the particles are in the same superfluid state. And this is the corresponding nonlinear equation that you get, but you can also do it by doing the variational procedure with this many-body wave function, and you will get the Gross-Pitayevsky equation, where it's basically a Schrödinger equation, but then you have additionally this nonlinearity that comes from the probability of the wave function itself. And for fermions, if we have exactly n orbitals, so the number of orbitals equals the number of particles, then we can capture this as a mean field theory in which every particle moves into the mean field of all the other particles. And this is equivalent to a Hartree-Fock equation, where you have your many-body state as a single determinant, as Slater determinant. And then the corresponding equation of motion would be the Hartree-Fock mean field equation, where you also have here as a kind of like a renormalized Hamiltonian that contains the one-body part as is, but then contains kind of direct and exchange terms from the mean field of all the particles. So those are special cases that we can get from MCTDH-X, but MCTDH-X is more general.
But they are always nonlinear equations.
These are nonlinear equations, yeah.
And could it be that that causes some problem when you try to optimize the orbitals that you, with nonlinear equation, you don't need to find a solution. You can get into some periodic doubling or something.
So what is the question exactly?
Do you know, like when you want to optimize and find the orbitals at every time step?
Yeah.
Could it be that you actually don't find them because it's nonlinear equation?
No, so those are special cases that are contained in MCTDH-X, right? So if you have more orbitals, then you're just going beyond that picture, you're just making it better.
Yeah.
So
Yeah, probably then you will not have a problem with like.
yeah.
Yeah.
I mean, there is always the question of whether you need, you're doing a calculation with enough orbitals, right? But then there is a way, as I show right now, to check whether you are converging the number of orbitals, to check whether, you know, your numerics make sense or you need more. So these two considerations that we just said imply that for fermions, we must have at least an m, a number of orbitals that is at least as large as the number of particles because of Pauli exclusion. But for bosons, we can have m that is smaller than m. We can have m equal to 1, and then we're in the Gross-Pitayevsky case. And strictly speaking, an exact representation of the many-body state is only achieved when you have m going to infinity. So you have, you know, infinitely many orbitals that you can use. But in practice, and this is very, very important to note, a finite number of m can be sufficient to solve the problem numerically exactly. And this is what you will do in the tutorials today. You will see that you can obtain a numerically exact solution in the sense that you have a problem that has an exact solution. In the case for today would be the harmonic interacting model. And then you can see that as you increase the number of orbitals, you converge to the exact same energy, the exact same density, and so on, within a given decimal places in the exact result. So then a finite number of orbital is enough to get accuracy up to, I don't know, 12 decimal places, for instance. And then you can say that it's numerically exact. And this is, of course, also true for the time-dependent Hamiltonians, and the harmonic interacting model can also be time-dependent. So this also comes, so now I come to the point that Jonas was mentioning. So this allows us to introduce the concept of orbital convergence. So what we do is we first run a calculation, let's say 5 orbitals, and then we see how the population of the orbitals behaves. If the least occupied orbital is still macroscopic, then we are not converged to the full solution because there's still room to add more to improve the approximation. So what we do another run with 6 orbitals, and then with 7, with 8, and so on. And then we try to understand, we look for the population, and we try to understand whether at some point the population of the least occupied orbital becomes negligible. And at that point, we then declare the problem converged in the number of orbitals. There is other means to check convergence with variances and so on. It's a bit more sophisticated, but I think for today, for a crash course, this is the best criteria that we can use. Just a quick summary now of what is MCTDH-X and what is not. So it is an approximation. So we always have to remember that it's an approximated method. But it can, however, converge to the exact solution as much as desired, given enough orbitals that you can provide. It is one of the best methods to treat many-body dynamics reliably. It is not one equation, it's many equations combined. It's not an extension of mean field theories. It is a fundamentally different technique. It's based from a fundamentally different starting point, and it contains these mean field theories as special cases. And it is not exact diagonalization. That's what Lucas was talking about. It uses this adaptive time-dependent basis. So it is completely different because it's optimized in time to the problem. But at the same time, it's not a one-fit-all treatment. It's not designed to tackle any arbitrary problem. It does not perform well when you have very strong interactions and or a very large number of degrees of freedom. So typically, the best performance is obtained for small or medium-sized systems, with up to 20, 30 degrees of freedom, which have not very large nonlinear couplings. And I think that's all here. We discussed this already. So I think it's enough for the first presentation. We can have some fika now.